Essentially, the commutator is quite important for quanta. So here I'm going to show you one example of how do we do that. So folks, if you write this down, this is sort of generic way we do that. For instance, if I have a commutator A, B, C, like this. And it has two ways to do the calculation. And I want to show you what these two ways is doing. And it's very important for us to do the calculation. So we have two ways. Way one works for any cases. Works for any commutator. So this is going to work for any commutators. So it works for any commutators, but it's a little bit non-trivial in the sense that, so when we want to work out this commutator, what we do, we express this term in terms of the commutator, the A, B, C like this, and B, C, A, and the back like that. So first we write them out. This is just a commutator A, B, C, and B, C, A. That's expanded like this. So it works for any time. But now, when you need to do, and this is, let's call it step one. Folks, could you add the step one? So step one, we express this commutator into these two terms. That's always the case. Commutator. Step number two, then we add auxiliary function, let's call it x of x. So in other words, this commutator, you cannot do anything with it. The next step, you're going to calculate and how large this one will be. That's the second step. So this is essentially the first term, you'll get this. Second term, you can get a b, C, A, F of x. And how large this one is going to be. And then you subtract from each other, subtract. So you basically, the first equation minus the second equation, and you will get an expression. So this equation minus that equation, and remove f of x. After you do the subtraction, you remove the f of x. So this is way number one. Works for any commutators. You're going to do it like this. So suppose you're A, B, C, and then you will do it like this. If you're A, B, C, D, do the same thing. Essentially, this was same idea which we have. Are we good on this? Are we good on? Can I get a thumb up? Everybody give me acknowledgement. Okay, very good. So essentially, doesn't matter how complicated this commutator could be. You could have an A, B, C, D like this. You do the exact same. That will become out A, B, C, D minus C, D, A, B. So that's what you do. And multiply by F. So that's all you need. And this is the first way. Now, way number two, not universal. This is not a universal, but sometimes it could be quicker. The condition is that if the simpler commutator is unknown, if a simpler commutator is known. A simpler commutator is known. And we're going to start with this equation. We're going to write the answer down over here. So you see here, it's A, B, C. We can write in this particular format, A, B, C, as we derived last time. And we'll move B to the front, A, C like this. So now, when I say a simpler commutator is known, what this means if your AB is known or AC is known, then you can plug it in directly. That makes sense to all of you? In other words, if I knew AB commutator is AC, you just simply plug it in. You do not need to do anything, and that would be much simpler. So the condition is that you must know A and B, or A and C. If you have more complicated, you must know each the simpler commutator must know. So this is the conditions, but otherwise you won't be never universal. So this is the comment that I forgot last time. All right. Any question on this? So now we're going to talk about our exams. And I'm cautiously, in some sense, optimistic. But there is one thing that I thought the students should get. Number 6 should be 100% correct. But some students still get confused. I really want to use this as example, number 6. So folks, could you go to number 6, please? Let's go to number 6. So I'm going to write down the answer over there. Folks, let's go to number 6. Yeah, everybody onto the number 6. And I thought this one should be straightforward, but not everybody got it. I think it is a good idea to explain it clearly, because this will be utilized. So what this guy essentially is asking for, this is number 6. So we have two wave functions. Psi, this is the superposition of the wave functions. Phi 1 plus square root 2 over 3, phi 2, like this. Forgive me, this is 2. All right. And phi 2, phi 3, these are the eigenstates of the polynomial box. We say this there. So these are eigenstates. They are normalized in this case. When time not equals 0, you will get another additional factor, which is over here, e to the negative IE 2t over h bar. And this is going to plug in. I think all of you did it correctly without any problems. So everybody did a very good job when you get time-dependent shooting. The stationary state. That's the part of it. And then it shows wave function is normalized. So watch carefully now this time. When we say wave function is normalized, which means we need to prove. We need to prove this equals 1. So this is the proof. So we need to prove this equals 1. And this is the way, and I saw a few of you simply square this wave function. That's not right. Because this one here has two meanings. This would be star like this. Second meaning is that you need to do the integral over dx like this. So this is direct notation. In Schrödinger wave function notation, we're written in this following format. So now I will continue to use the Schrödinger the direct notation, make things a little bit simpler to write. So we're going to use that, and I want to show you why this equals 1 here. So, and I'm going to first write this part out. Write this part out. So this will be t not equals 0. I'm going to first write this part out. So I'm going to write over here. Remember, this is a bra. This is the bra case. So in other words, all of this will be bra. So it's going to square 1 over 3. This bra has a conjugation involved. Did you see I have a negative here? And this will become positive E2 TH bar. So this term, now this becomes bra. That's what becomes bra part. So this term is this term. Everyone's good so far? Everyone's good so far? So this is the bra, what we have. The second term here, square root 2 over 3, and then we get also positive there, E 3t h bar, and we have a bra 3. Okay. So this part is just show you the bra part is my bra part over here. All right. Now the bra part is not finished yet. We have a cage part. Now the cage part comes up. kth part is just this part comes out. So we're going to write it over here. That's where the kth part comes. Now the kth part is the wave function itself. In other words, we use the vertical line here. This vertical line is the same vertical line here. And then we continue on this. I'm not going to skip any step whatsoever. E to the negative I e. And then we have a kth. Let's go to 2 over 3 e to the negative I e 3 th bar. And then like this. So that's actually terms like this. Are we here so far? For those of you, it's especially for those of you who got it wrong. Did you guys see where do you need to do? You know, you have these two terms multiply each other. Now you're going to do the multiplication. You have term A multiplied by term B, term C multiplied by term B, and you also have D terms. So in principle, you have 4 terms. You see, you have 4 terms. You have these crossing terms, A times B, C times B, C times B, C times D, like these. Total, I have 4 terms. Let's do the AB terms first. Let's do AB terms first, which is this term and that term. So when we do the AB terms, 1/3 comes out with square root is gone, and then these 2 terms cancels out. One positive, one negative cancels out, and then this will be phi 2. Another one is phi 2. So AB term becomes this now. All right. Are we good so far? Can I get a thumb up, everybody? You good? Okay. Everybody's good. So AB term is like this. Now let's do the AD term. I'm going to write a little bit higher here. AD term. AD term, we have square root 1 over 3 and square root 2 over 3. And we have this term multiplied by that term. They cannot cancel now. No longer can be canceled out. And this time that, this will be phi 2, phi 3, like this. Folks, what is phi 2, phi 3? Phi 2, phi 3 equals what? 0, exactly. So this term equals 0. In other words, all these crossing terms, like C, B, these all terms come. So CB, this is also 0 for the same reason. They all come. So what you end up with, you only have a CD term. CD term. CD term will be 2/3 times, again, phi 3, like this. And this equals 2/3, like that. So, and this equals 1/3. You see, 2/3 add 1/3, of course, equals 1. So, if we add these together, it equals 1. That's how we do the calculation. Now, the second part is we're looking for, we don't need to zoom anymore. Let's stop the zooming. Oops, okay, exit zoom. The second part is compute the expectation value of the Hamiltonian operator. Hamiltonian operator, essentially we plug the Hamiltonian here, like this. So everything stays the same. In other words, these crossing terms still gone. There's no crossing term. And this term will become, so you have E2 in the front, like this. And this term here will have E3 in the front, like this. So then the expectation value of the Hamiltonian operator, so this, that add up. So essentially there will be 1/3 E2 plus 2/3 E3. And that's all you do. And ask you why, to explain why it is not time dependent, because this is stationary state. Stationary state, the eigenvalue of energy eigenvalue is always the same. That's called stationary state. And to compute the expectation value for Px, and this is the exact same thing as in our homework. We got someone forgot realized the P itself. Just be careful. P itself, this P. If you plug the P here, let's get P sub x like this. P sub x, the diagonal term, like AB term, is going to be 0. Because if you put P here, so this transition matrix element has to be 0. So in other words, the diagonal term now is 0. But all diagonal term, original 0, this is non-zero. So essentially you will see like this, Px, this won't be equal to 0. And this is the same reason, this won't be equal to 0 when you have to put Px there, like this. So that's why yes.
Where's the E1 and E3 come out of?
How I get E1, E3 come out?
Yeah.
Let me show you. I'm going to rewrite this part a little bit clearly. You understand the coefficients cancel, so there's no problem with that. Let me show you. So A, B, Hamiltonian, B like this. And so we have 1/3 in the front. Here is a phi 2, H, phi 2 like this. So this is the one we have. Okay. Are we good?
Where did the Hamiltonian come from?
Yeah, this is the way you plug the Hamiltonian. You with me so far? In other words, let's back up a little bit. When we plug the Hamiltonian, so let me erase some part of that. Maybe not easy to visualize it.
Oh, are we on part B now?
No, we are on the part. We're on part. The part B is already finished.
Okay, I was just lost on that part.
Oh no, yeah, part B already finished. Part B is is this guy's here.
I thought that was the proof of normalizing the wave function still. That's why I was getting confused.
Oh, normalizing the wave function is already finished because when we have 1/3, you remember without E2, this 1/3 plus 2/3 adds up equals 1.
Oh.
That's normalized.
Oh yeah.
So that's the part one. And any other questions? Any other questions? So that's how do we finish the calculation. All right. Next week we have a quiz. So on the material in the chapter 3. So make sure get ready for that. Okay, sounds good. If you still have a question, if I grade something wrongly, please do let me know. I will be more than happy to look that over. And so this is the one which we left over. And today I'm going to start with the number 1. And this is a real solving the harmonic oscillator problems. And this time we do the more rigorous. Last time I showed you how we do that. This time we're going to talk about. So last time is the Hamiltonian, which I showed you here, Hamiltonian cell. That's where Hamiltonian is. And today our job is going to be called, let's call it number 2 instead of 1. Today is already 1. Look at the ladder operators. So this is called the lateral operators. The lateral operators are auxiliary operators. They are not aiming to find the entire solution, but to help us to find the solution. The lateral operator, and we use the letter A to representing that. So the A put a hat on the top. That's called a lateral operator. These are all another a-dagger. These are all auxiliary operators. So these are all auxiliary operators, and they utilize it. We utilize in the following way. Now let me show you why this comes out. So we're going to show you now. We're going to rewrite Hamiltonian. And the Hamiltonian is a px hat 2n plus n omega squared x hat squared. I repeated what I just wrote before, so they're exactly the same thing. I didn't do anything with that. Now this time we want to make this expression looks a little bit nicer. So then what we do, we pull out of this 2m out. You know, each of these terms pull out 2m. So then you will see immediately for px squared plus 2m is out, but now you have another m in the front. and then have 2 is in 1/2 is in the front. Omega squared x squared like this. Did you guys see why I did this? Did you guys you see what I did this? Before my m just single m, right? But here's m squared. So therefore, in my mind, I have term like x squared plus y squared. So the terms is just simply look like this. Now what I do next, and I'm going to split this into 2 terms, two different terms. Folks, did you see I have a 1 over 2m? I split over this 1 over 2m equals 1 over square root of 2m. And then I have another term. Folks, I'll leave some space here. Like this. So there's no problem. I can always split this into 2 like this. So multiply each other. So now the first term, did you see I have a square like this? I make them without square. Take square root, essentially what I did. Like this. The first term takes square root. Notice that I move the second to the front. And plus px. So originally I have a square, but now this term. Of course, this cannot be correct. So then I want purposely, and watch carefully. This part is a very top secret. Let me write and use different color. We purposely insert this I. Px like this. Just be careful. We put another I, which is blue color here, directly there. And the second term, I would add m omega x hat minus blue color I, and then I have px. Like this. So that's the expression which we have. So we are just rewrite this particular format. And of course, it cannot be equal to each other immediately, because it must some kind of extra terms involved. That's not that critical important. And then over here, we must have some extra term. We don't know whether extra term that will be, so I just call it constant. And this is the classical number, not a quantum, classical number. Not a quantum number, so it's not an operator. So I must have this extra term comes out like this. So essentially what we did was we used the same split as we did last time, just split it into the 2. But we don't like this term. You see we have 2ab. We don't like this term. And this is a job done by, I'm going to write this down. Folks, leave some space here. This I is to make sure we have a commutator xpx. So this little I there is to make sure we will have this commutator directly. I checked all of those books actually done before. They always heuristically to give this idea, how do you get this, but I think this is the one that we propose here is actually a little bit simpler like that. So again, we put I here and native I there. And you can try, Cody, if you remove this I, if you remove that I, if you remove these 2 I's, you will end up with results we have a more complicated than without I. So that's what it. You also realize you must put in a negative sign there as well. Because if you put a positive sign there, then you could imagine you have a px, what you call px, x times px. If you get a positive, you will have px like this. Remember, we assume it is positive, and then you have another px x hat. And this term, you cannot simplify it. This term you cannot simplify further. But this term can, because this term is x px minus px hat x. So that, did you see I have a name sign here? Did you see our name sign? And this name sign is this name sign. If you had a same positive sign, sorry, it won't work. So that's the main goal here, why we want put this name sign. Now this expression still not perfect because it has a dimension. So what we do next is that, folks, we're going to divide by h by omega, this term here, and also this term h bar omega, like this. Now remember, we denominator we have h bar omega, so therefore the final expression down over here, folks, down over here, we're going to plug h bar omega over here. And I will explain why we will do such complicated situation. Well, here's something very interesting. Here's something very interesting. This term is dimensionless. These two terms are dimensionless. There is no unit. There is no unit, essentially, zero unit. This term is dimensionless, and this term is dimensionless. And you may wonder why you add this. Well, you want to make it dimensionless. While the last term here, this unit of energy units. And this is the energy units, and we like it. Essentially, you have a bunch of terms in the front, but you have energy units, but Hamiltonian is the energy. So that's why, how do we do that? The first term here we called a-dagger. Second term we called a, also a itself, and the second term is a-dagger. So that's the equation which we end up with. Again, we didn't do anything, just split it into two, but we have some kind of extra term come out. That's what we did there. Are we good so far? Are we good so far? So that's how do we derive it in this particular heuristic way. So this is how we get it. Now we're going to start with these equations, and I want to show you a little more explicitly. So why we need to introduce this. So this is a way for us to compute the harmonic oscillator problem, and without doing too much complicated things involved. So this is now we're going to show you on this board. So we're going to show you directly. So now we're going to continue on these dagger operators. So that is the one which we are going to do now. So we're going to write them out more explicitly. So this is the a hat equals square root 2m h bar omega m omega x hat plus I px hat. And these two operators, which we call lateral operators, and the lateral operator, the dagger part, this is rather straightforward. If it daggers for the front, because this is the Hermitian operator, so it doesn't change anything, because so this will be omega x hat, and this will be dagger self, so you know what's x dagger equals x. So now this part doesn't change. But it does change the I, from positive I to negative I. And this, again, the Hermitian operator doesn't change, so this will be still px hat. So this doesn't change, these two operators. And these two operators are called auxiliary operators, called lateral operators first. And you can show a dagger not equals a. So these two not equal to each other, and then pretty clearly you can see that. But this has a positive, this has a negative, they won't be equal to each other. And if you have a minus a dagger, this minus that, so this minus that, you will get twice of square root 2m h bar and px dagger like this. So you see they're not the same. If you add them up, you're going to have the x square root of 2m h bar omega, like this. So these are the operators you can see. And the a and the a-dagger has no meaning by itself. But when they're operating on the same, if they're collaborating with each other, it has a meaning. I'm going to write this down. A hat dagger have no meaning, no physical meaning. Physical meaning. But when they present together, are present together, they do have physical meaning. So in other words, you cannot simply use a single ones to create something physically meaningful, but when they're present together, it has meaning. So just like present together has meaning, present together has meaning, but separately doesn't. So that is the case which we have. And this is not a Hermitian operator. It is not a Hermitian operator. So we'll quiz you next week and make sure that it's not a Hermitian operator because they're not equal to each other. So this is the way which we have. And you also can prove, this is a very important relation. You can prove this very important relation. A hat, a dagger, this equals 1. And you can rigorously prove this in class will be something like this. So a dagger a equals 1. In other words, if a dagger a plus minus a dagger a, and this equals 1. So this is the first important relation between these two. And there are a whole bunch of other relations which we won't cover, and this is left over as an exercise for the home exercises. Most importantly, the a-ladder, this means if you apply an energy, this will decrease the energy. Sometimes we simply call it climbing down the ladder. Climbing down the ladder. If the ladder representing the eigenenergy, for instance, here the ladder 1, ladder 2, ladder 3, like this. So in other words, each application, a-dagger will make the energy lower. A-dagger, not a-dagger, a itself, a-hat, energy, each application will have energy lower like this. While a dagger is the other way around. So this is the a dagger. Increase the energy like this fashion. So this will be a dagger is going to be increased energy. That's why the climbing the ladder is utilized in this particular format. Are we good so far? It's a little bit abstract in some sense. Did you guys feel it's a little abstract? We have introduced an extra step. The reason why we have to use this will be important is to understand the next step, which allows us to see. So we're going to utilize this information to find a wave function first. But before we do that, I want to show you the last item. How do we do the calculation in this format? So this is the ladder operator. And one last thing which we will show you is the next expression. So this is the last one. Once we have this particular ladder operator, we can rewrite our Hamiltonian in the following format. The Hamiltonian can be written in the following way. A dagger A plus 1/2 h bar omega. Did you see I wrote down the classical constant? You guys see here? Did you see the classical numbers here? This particular number now has a value. Value is 1/2 h bar, like this. The ladder operator now becomes part of the Hamiltonian operator, look like this particular shape. Now I want to explain 1/2 h bar omega. 1/2 h bar omega is very important consequence of quantum mechanics. So this particular part is quite insightful for us to understand. And this is called a 0 point energy. This is called 0 point energy. What this means is that if you cool down the system to 0 Kelvin, suppose you one day, of course you've never been able to do this. 0 Kelvin, it's absolute 0 Kelvin, but the system must still have 1/2 h bar omega energy. And this is bizarre in the sense that in the classical physics, if you put the ball under the bottom of the well, you get a 0 energy, so it does not have potential energy, doesn't have kinetic energy, 0 energy. But for the quantum mechanics, well, you have this amount of energy. What's the reason? What is the reason? Why we already cooled down to the 0 temperature, but he's telling me you still have some energy? Here's the reason. This is Heisenberg. Uncertainty principle. This is the Heisenberg uncertainty principle. In a Heisenberg uncertainty principle says the following. You look at if you have a position and momentum. Remember, position and momentum, they're not permittable. So in other words, this part, you see the position and momentum. This equals RH bar, like this. Now, if at one time your kinetic energy and omega squared x squared is hat, if this is smaller, and then this is the potential energy. Now, kinetic energy in this part. So in other words, when they are not permittable, you cannot get these all equal 0. Because if assuming you let's say x equals 0, let's assume x equals 0, then if x hat equals 0, then px is going to go to infinite. Because you remember delta x, delta px must be larger than or equal to 1/2 h bar. If you make this guy equal 0, this has to go to infinite. So therefore, it will be no case after both will be goes to 0. I'm not sure you guys get this idea amount. In other words, regardless whether you have the 0 temperature, but the system cannot goes to absolute 0 energy. And this is the point called the 0 point energy. And let me look at the experiments. So this is experimental evidence. Experimental evidence of the helium cannot be a solid. Helium never be a solid because it's like jiggling around all the time. Cody, just like jiggling around all the time. When you jiggle around all the time, your maximum you could get a liquid, but not solid, because it has a much lighter mass. So therefore, it never becomes a solid. And this is a consequence of that. So again, let me summarize what we learned here. The ladder operator allows us to gain these energy levels directly without solving actual Schrödinger equation. We're going to go down, we're going to go up. It also allows us to get the eigenenergy out. And then finally, we also got this 0 point energy. And that's the beauty of this. So now what else we could do? And this part becomes even more interesting, and you can see me right now. So in other words, what will happen if we use a lateral operator and try to develop something which is quite useful? So this is my item number 2, and we're going to item number 3. So item number 3, we're going to show you. In fact, we can get something from nothing. And this is quite interesting. So this is item number 3. Find the eigenfunction. Find the eigenfunctions. And this is I found this part is extremely interesting, very, very interesting. And I'm going to show you systematically what that is. I'm going to denote the eigenstate. It's called phi sub n. Eigenstate called phi sub n. That's the eigenstate. So now, suppose the ground state is phi sub 0. So here's a quantum number n equals 0. Just be careful in comparison with the last chapter. Last chapter, n cannot be equal 0. Here, yes. So that's the difference. Okay, so in other words, last chapter, n always starts from 1, 2, 3, all the way up. But for our bosonic features, n can equal 0. So that's the difference. Remember, this is the ground state. All right? Since we discussed the lateral operator, each application... Yes, go ahead.
So in the previous examples, was n equals 1 the ground state for those cases, or is there a minimum excitation?
Yes, exactly. So for all the last chapter, anything we discussed, n equals 1 is ground state, n equals 2 the first excited state, n equals 3 the second excited state, like these ones. But here's ground state n equals 0. That's a huge difference. If you're interested, let me write this down. Bosons. And this is how the bosons typically have this particular features. N equals starting with 0. And gradually piling up like this. So again, this is the ground state, phi 0. So that's it. And of course, it's a function of x. Has to be a function of x. Now, did you see we use this lateral operator that's already down this? So let's say this is my ground state. Let's say this is my ground state. Okay. So now you can see a hat applied on the ground state. This has to be equal 0. Because this is already ground state. You cannot be lower than the ground state. So this function has to be equal 0. If this is the lateral operator, each application we're going down. Now, just for your curiosity, if I apply the lateral operator to the first excited state, did you see I have a phi sub 1? This will be proportional to phi sub 0. That means I lower the energy. On the other hand, I have a-dagger on the ground state, and this is going to be proportional to the first excited state. Okay, so this is the ground state which we have. But if you originally had been the ground state, when you apply it on that, of course it has to be equal 0. If it's not equal 0, this means this state you applied on is not a ground state. Does it make sense to you? So this cannot be ground state if it is not equal 0. So if it is a ground state, it must be equal 0. Now, once you accept this point of view, you will find something very remarkable. So we're going to use this expression applied on the phi, like that. Now, did you see coefficient doesn't matter because my right hand side is 0. So I'm not going to write out this coefficient. Okay. Yes. Question.
So if you have the second excited state, is that going to be proportional to phi 0, or is that going to be proportional to phi 1?
Let me write this entire thing down. Suppose you are interested in the phi 2, like this. Which operator you are interested in? You are interested in a-hat or a-dagger?
I figured that particular question should be a-hat, so...
A-hat, like this. Yeah? So then this is going to be proportional to phi 1. So this is going to proportional to phi 1. So in other words, phi 2 is going to proportional to phi 1, Alex. So that's what you'll get. Now, if this is the real ground state, we just put there. Coefficient doesn't matter, so I'm going to write this down now. So my A is just equal m omega x hat plus I px x hat. And this equals 0. Again, my throwout of coefficients doesn't matter. So this equation can be written out completely. And in the Cartesian representation, x hat is just x. This part we know now, negative h bar. So we have a partial x, like that. That's my momentum operator. And phi 0 equals 0. I, negative I, this becomes just simply 1. So therefore you will see n like this, h bar. Now since this only depends on the x, so I can change the partial derivative to full derivative, dx, and phi like this, equals 0. And this is our differential equation. This is our differential equation. And this is the real simple to solve it. Let me show you. Let me have all these terms divided by h bar. So this h bar is gone. Like this. So I move this term to the right hand side, I will get a negative sign. So which I'm going to write on the top here. So this will, you will see me in the following format. d phi 0 over dx equals negative n omega h bar x like this. Are we good on this part? So now all we need to do, both sides times dx. So my left hand side, oh, forgive me, I have phi. Okay, so this is, here's a phi 0. So both sides divided by phi 0, both sides times the dx, so I will end up with the d phi 0 divided by phi 0, and this will be n omega x, there's no, there's h bar there, and dx like this. And this integral is extremely simple. What is the left-hand side we get? To the integral. Okay, what's the left-hand side we get?
Natural log of phi.
Exactly, that's logarithmic of phi 0. What about the right-hand side, Alex? Alex, what's the right-hand side? Exactly, should be x squared over 2. That makes sense. So then we get a phi 0. Of course, then we have a coefficient in front. It's a final renormalization coefficient. So this will be have an a e to the negative n omega 2 h bar x over 2. Folks, this is our eigenfunction for harmonic oscillator. This is a Gaussian like this. Very, very beautiful Gaussian like this shape. It's a Gaussian x. And that's a harmonic oscillator. How do you like it? This is a really elegant way to solve for this. Of course, you could do the harder way. That's much harder to do that. And this is our first eigenfunction. If I want to calculate the excited state, let's say phi 1, all I need to do is a-dagger apply now the phi 0. I get a phi 1. Did you guys get it? So then all these subsequent, all these levels will be raise up, raise up, raise up, raise up. That's all I need to do it. That's it. Essentially, I can stop here now for this chapter because I already got this one, the eigenstate. And then eigenvalue, which is even simpler, which I'm going to talk about next class. The eigen, for those of you who cannot hold on the eigenvalue here, I can quickly plug in something here. So do you see I have a-dagger a here, a-dagger a here, and this part you're going to see me writing on Friday will be n. So that is our ground state wave function. Eigenstate function. And that's it. So we solve the harmonic oscillator this way. Any other questions? Yes?
So you got the exponential from exponentiating both sides to get the L in dot, right? But where'd the A come from?
Oh, this A is due to the limit. Let me show you a little more detail. Let me plug in one step from here to there. Let me plug in one step from here to there. Okay, let me plug in one step. So let me plug in from here to there. From here to there is in fact, it should be look like this. This left-hand side, minus 5 from negative infinity, like this, positive infinity. It's because this guy has a limit. Let's say you start from some place to, let's say, cut from negative something all the way to x like this. And this will be lower limit. You will have term look like this. Lower term look like this. Make sense? And this term, when you write them out, you get it like this. Because this is a constant anyway. This is a constant anyway. Doesn't matter. But this would just look like phi constant. Sorry, I have to write a constant here. And write out this constant. And then this will be divided by a constant. And this constant is just a.
Okay.
Yeah, that's it. So usually this stuff essentially limits from one to the other. That's what we did here. And same thing on this side, from 0 to infinite to x. So that's why you get x. And the infinite part is going to 0 because x squared positive negative infinite is always 0. So that's why you did not see that term. It's just putting the a factor in front. I jumped a slide a little because I'm angle plus. I don't want to extend further. Any other questions? Any other questions? Okay, this is the hardest class up to now because we cover quite a lot of ground. So just make sure you comprehend this, and that's it. So we're going to talk to you guys on Friday, and Friday we'll talk about the energy part. So that is my plan. All right, I'm going to end here.